Hello, everybody. Welcome to today's current seminar. Today we have one speaker, one talk. Our speaker is Dr. Guang. He will be giving a talk on fPINN-DeepONet, an operator learning framework for multi-term time-fractional mixed diffusion-wave equations. Prof. Guang Lin is an Associate Dean for Research and Innovation and the Director of Data Science Consulting Service at Purdue University. His research focuses on cutting-edge artificial intelligence and scientific machine learning. He's a full professor in the School of Mechanical Engineering and Department of Mathematics at Purdue University. Lin received his PhD from Brown University in 2007 under the supervision of Dr. George Karniadakis and worked as a research scientist at DOE Pacific Northwest National Laboratory before joining Purdue in 2014. Professor Lin has received various awards such as NSF Career Award, Mid-Career Sigma Award, University Faculty Scholar, College of Science Research Award, Mathematical Bioscience Institute Early Career Award, and Ronald L. Brodzinski Award for Early Career Exceptional Achievement. With that short introduction, the floor is yours and you can start your presentation.
Yeah, thanks for your nice introductions. Also, thanks for George's inviting me to give a talk at the Brown University Crunch Group webinar. So today I'm going to talk about operator learning of the multi-term time-fractional partial differential equation using our fractional PINN-DeepONet. So this is a joint work with my students, Bing Hang, also Bing Hang Lu here, and also Chris Moya, my postdoc, and also Zhaopen Hao is my visiting students. And so you can see the later is the link for our preprint. So you can, if you're interested, you can click and find our preprint. So first, let me introducing some the background, just in terms of someone may not be familiar with the fractional PDE. So a general form of the fractional PDE can be represented. So in particular, in this work, we focus on time fractional PDE. So on the left, you can see, so the basically this D alpha T is the time fractional representation, and this alpha could be from 0 to 1 or 1 to 2. So the typical fractional derivative could be the Caputo derivative or Riemann-Liouville derivative. So the fxt is a source term, and the omega is represent the spatial domain, and L is the spatial differential operator, such as the Laplacian operator. So let's first look at some application of a fractional PDE, and there in the mathematical field. In the mathematical field, so it including the first one application, it could be the fractional calculus, right? The fPDE basically extend the classical PDE with a memory effect and the long-range interaction, because it includes both integration and the differentiation together, right? So the integration will represent the memory effect and the long-range interaction. So also the second area, so is the numerical analysis and approximation theory. So FPDEs require some special numerical method because it's its own singularity. So we have to develop a very specific finite difference and finite element of spectral method. And also, there's a researcher also apply in operator learning technique and also physical informed neural network. So George is pioneer in this area. So in another area is George and I have applied the fractional into the fractional epidemiology model for COVID-19 prediction. So this is a paper I work with George. We developed this integer and fractional order epidemiology model using the physical informed neural network that is published at the Nature Computational Science in 2021. So in terms of the fractional PD application in the physical field, so that first one, we can apply to anomalous diffusion and transport. The FPD describe a subdiffusion if the derivative order is between 0 and 1. Also, it can be represented superdiffusion if it is from 1 to 2. And it has application in geophysics, biophysics, and climate science. And also, the fractional PD can be applied to the fractional quantum mechanics, such as the generalized the Schrödinger equation with fractional Laplacian, and also application in quantum transport, optical lattice, and the wave functions. So the fractional diffusion equation is a simple representation as the d alpha t equal to the second order, the d Laplace u. So here the d is the fractional time derivative with the memory effect. So in particular, so let's look at some literature. So some previous work on time fractional. So here I just name a few. There's many publications. So one publication is by the reference 3. They developed a full discretization scheme using the Gaussian finding element for spatial discretization. And the reference 4 proposed a finding difference scheme and provide its theoretical analysis. And the reference 6 is by my friends, Dr. Sun. They did the introducing the method of order reduction, and which introduced the subsequent approach to solve fraction PDEs. So George and Guofei, they derived the fractional pin, so called the fPINN, to solve the space-time fractional advection diffusion equation. So the idea is to develop a neural network and also apply the fractional derivatives, right? So then you compute the residual of the fractional derivatives and compute the loss function, then evaluate the convergence, and back propagation to to do a fractional pin approach to solving fractional equations. So this work is George published at 2019 at SIAM. Okay, so in this work, let's first define what we want to do. Is we want to solve fractional PDEs. So the non-local nature of the fractional order derivatives make the design of a stable and accurate method challenge. And so in particular, we are looking at the fractional order, alpha and the beta. The alpha will be vary between 0 and 1, and the beta vary between 1 and 2. So then this is we call the multi-terms, right? So we have some, one kind of fractional order, we have the other kind, mix them together. And we want to construct a DeepONet, we call G theta, to approximate the solution operator, G Dagger. So we want to map the U to the S. The U could be the falsing, could be the initial condition, and also could be the boundary condition, and also could be some parameterization in the PDE. And the S could be, and also it could be the fractional order alpha and the beta. So eventually we want to map to the solution, this forward problem. And also we can do it in the inverse way to, if you give me the solution, I can inverse the fractional order or the source term. So let's look at the architecture of DeepONet. So the DeepONet architecture represents as following. So we have a branch net and also a trunk net. So the branch net, we're using the U. So that could be the initial condition, or could be the source term, could be some parameter in the fractional PDE. And for the trunk net, we input is y, that could be time and a spatial coordinate x and y, z, for example. And so the training parameter is the hyperparameter inside the branch net and also the hyperparameter inside the trunk net. So we combine these two together, then do a dot product. So the branch dot with the trunk and do a summation, then this is we will obtain the prediction of the solution yield. So this is the basically architecture and of the DeepONet. So the key contribution of this work is following. So we utilize an L2 approximation method to approximate the fracture PDEs with a fraction order alpha I in the range of between 0 and 2. Also, we extended the fraction order alpha to distributed order. Basically, the alpha will be a function of x, t, or just a function of t, enable more flexible modeling. And also, we developed an operator learning framework to solve a wide class of fractional PDEs. We called fPINN-DeepONet. And also, we conducted extensive experiments to learn on the alpha in the fractional PDE inverse problem and demonstrate the effectiveness of our approach. Okay. So first, I want to show you basically the approximation of our. Let me see what's happening. Okay, so okay. So we want to approximate the solution operator G Dagger for multi-term and the time fractional mixed diffusion equation. So here we have two terms, right? So we have K1 is just a constant times the first time derivative is the dt alpha I. And the K2, we have also another is dt beta I. So alpha I is between 0 and 1, and the beta I is between 1 and 2. So the idea is mixing of two different kind. Ones represent the subdiffusion, and for the alpha I, and the beta I represent the superdiffusion. So that could be exist in the applications such as pulse media. So you have some so in the pulse, there's you have the pulse structures, very complex pulse structures. So in the rock, existing some subdiffusions that represented by the alpha I, but in the crack between the rock, that could be the beta I. So that we want to develop this multi-term time fractional model, want to represent this kind of complex pulse media flow. So here in this example, we want to this time fractional we can using a Kobuto fractional derivative to represent this. So following, I will give you some basically talk about the first one we're gonna looking into is a one-dimensional, basically time fractional mixed, diffusion wave equations. So the two-term mixed term, the subdiffusion model is the first term called the dt alpha. The super diffusion will be the dt beta. So we have a Laplace term on the right plus a source term. So then this is the initial condition and the bounding condition. So here the omega will be between 0 and 2L, K1, K2 are all constant. The alpha 1 will be 0 to 1, and the beta will be 1 to 2. So this is the typical of two-term, okay? So the time fractional multi-term fractional equations. So let me first introducing a few traditional methods I want to compare. So compare with traditional theoretical work we have done and how we can take it to develop a neural network approach. So first we can develop some compact finite difference scheme. So if we define the average operator AX, right, this AX VI represented the stencil we are looking at is compact finite difference scheme. All right, so this is basically a 3-point stencil represent the average operator AX. Then we do the spatial digitalization and with the initial condition and the boundary conditions. So then we can derive the compact finite difference scheme. So that's this equation. We have K1 AX plus K2 AX, right, equal to the Laplacian equal to AX FIN plus the actual term. So this actual term, the last term, is come from the L2 approximation of the time fractional, the delta t beta, right? So that's the additional term we obtain. Later on, I will explain how we get this last term. So then come with this, with these conditions of the parameterization, we can using that to kind of derive some convergence theory. So if in the spatial digitalization, we're using a 5-point stencil to represent the U and two stencil representing time, then in the derivative of the partial U partial X, we're gonna have the 6-point stencil. And so the partial T, we're gonna have the 3-point stencil. With that, then the solution of the solution using this compact scheme will have such convergence rate. It's the convergence will be less equal than C times the tau plus h to the fourth. The tau will be the time step you choose, and the h will be the spatial step. So it will be bounded basically in the spatial is fourth order, in the time is just first order. So that's the convergence analysis we are being able to obtain using the compact scheme. So I will not go into detail for the proof. So here we also can extend this to two-dimensional multi-term fractional PDE. So consider we can generalize to this two-dimensional case. So then we're gonna have both Laplacian in X and Laplacian in Y plus the F subject to the initial and boundary conditions. So we did both 1D and 2D in this case. And we also can present the implicit compact difference scheme for this problem. So then we can derive this, this K1 AY AX delta T alpha plus K2 AY AX delta T beta. So this then we do the implicit, and we have this actual the last term. I will explain how we obtain this last term in the next few slides. So we're using the so-called L2 approximation to approximate the time fractional order alpha. We know this alpha is between 0 and 1, so we can approximate the time fractional Coupeau derivatives, for example, right, in terms of a summation of the basically using the finite difference, like a UTK minus the UTK minus 1 times the coefficient an minus k alpha n. So here is the ak alpha n can be represented as k plus 1 to the 1 minus alpha n minus k power to the 1 minus alpha n. So this is so-called L2 approximation. So the idea is it can approximate the fractional time derivatives using a summation of the finite difference approximation. So this is for the alpha between 0 and 1. And we also can do for beta that is belong to 1 to 2. So, but however, you will see, so by using the L2 approximation for this beta between 1 and 2, we're going to obtain is two terms. So you can say the first the delta beta un, then minus this 2 bn minus 1 to the beta over the tau beta t minus 1. So this expression were obtained. So that's why in my previous presentation, so that we have this last term. This is because we have a beta that's belong to the 1 to 2. So using the L2 approximation. So this bk beta n, is equal to the k plus 1 to the 2 minus beta n and minus k to the 2 minus beta n. So this is the L2 approximation. So following, we're going to look at our fPINN-DeepONet architecture. So assume we have the similar to the classical basically DeepONet. We have a branch net and a trunk net. We have the U could be the source, could be the fraction order, and the Y could be the basically T, X, Y, Z. Getting to the trunk, and then we do a dot product, we get the G theta. Then we have the loss function. So we have totally 4 different loss functions. So the first one is the residual loss, representing the residual of the fractional PDEs. And then we have the boundary loss representing, we want to minimize the difference between the boundary and the prediction. And also the initial loss represent the prediction of the initial condition versus the given initial condition. And also the last one will be the data loss. So basically, whatever data you have, want to compare between the neural network prediction versus the data you got in the L2 sense. Then we sum them together, we obtain the total loss. Then then we evaluate the convergence. Also compute the gradient descent to do the back propagation to update the coefficients in the DeepONet. So the initial loss of the fPIN mainly consider the two main parts that we call the physical informed loss and also data loss. The physical informed loss consider the residual loss, initial loss, and the boundary loss, the 3 terms. And the first term residual loss can be calculated, by doing the L2 norm calculate of the residual of the fractional PDEs. So the fractional term, the dt alpha and the dt beta can be solved using the L2 approximation method already presented. So then the operator arrow can be calculated using just compare the g theta minus the ui, which is the observation point. So that will give you in the L2 sense, give you the data loss. So the total loss function is defined as the physical loss plus the data loss. So this is the loss function calculation. The following, I'm going to show you some numerical results. So first, we are looking at is a fractional ODE. So the idea is we'll consider a very simple fractional ODE, the dt alpha equal to f. So then the right-hand side f represented by this representation. So the fractional order alpha is within 0 and 1. So the input t is sampled using a graded sampling method and described using the 100 sensors. So our goal is predict the solution U is a forward problem. So then here is the results. So because the exact solution is just ut equal to t to the cube, and we use 10,000 training points, and the L2 error is 1.0 38 times 10 to the minus 5. And the left figure represent the basically the loss convergence plot. You can see the x basically number of epochs, and the y is the loss function. So you can see the loss function dropped very quickly. So on the right, basically showing a comparison between the exact solution versus our PIN predicted solution. So the green line, the blue line and the red line, they overlap each other. So that's basically this is yeah.
What is changing here? What is it? Why is it DeepONet? What is changing here?
Well, you changing means you mean on the right figure or left figure?
No. Can you go back to the problem?
Yeah.
It's a forward problem, but it's for DeepONet, right? So what is?
So this is just like the changing is the basically I have so the changing is alpha is a function of t. So the input my trunk branch was inputted alpha t, right?
I see.
So yeah, so my trunk is t. Then I want to put
Okay. Yeah. So alpha of t is in the branch. Yeah.
Yeah, alpha t is in the branch. Yeah. So then I can just show show the compare with the solution with if I vary the alpha. So this first example. The second example, we want to do ODE inverse problem for the fractional ODEs. So the idea is our goal want to predict the alpha t, and given the solution u. So the ut is the equal to the t to the cube, right? So the right hand side ft, right, is also given. So then we want to inverse the alpha t, and the alpha will be a function of t. So similarly, so the T, we're using 100 sensors to get to the input for training. Then the next figure here we want to show you is there's exact fractional order, the alpha equal to 0.5 times sine square t. So then we're using 10,000 training points. The L2 arrow is 9.2 times 10 to minus 5. So the axis, the left figure is the axis epoch, and the y is the loss function. So you can see the changing of the loss function. This problem is more challenging than the prior problem. That's why you saw the loss. It's not like a convergent right away, very smoothly. It has some oscillation going on here. And the right figure basically showing you the x is the time and the y is basically the alpha values, and we'll compare with the one we predict versus the ground truth. So you can see they match pretty well, except in the beginning you have some the transition, and the ground truth is very smooth. So our predicted ones are some at the transition point there are some variations there. So this is for ODE, right? But the challenge is that the fractional order is not just constant, it's a function of time. So the next we're looking at the PDE example. So we consider a one-dimensional fractional PDE with the Laplace term. So this is the equation. So this is a forward problem. So we want to predict the fractional PDE solution U given the alpha, and the alpha is between 0 and 1, and the right-hand side fxt is equal to this representation. So this is a forward problem, but it's PDE. So the alpha is also a function of time. So in this particular example, so you can see the exact solution is the t to the cube sine x, and so we're using basically 10,000 times 2 training points because so one time and at t and x. So the L2 we have 2 sensors. Each sensor we have a 10 to the 10,000 points. So the L2 related arrow is equal to 3 times to the 10 to the minus 4. So the left figure is the exact solution of U. The middle is our DeepONet approximation prediction, and the right is basically the absolute arrow plot. So you can see, so the arrow maximum is about like 0.025. We can pretend that. So so that's the arrow plot. So you can see match pretty well in terms of predicting the forward problem. Now let's look at the inverse problem. So we consider the one-dimensional fraction PD with a Laplace term. For the inverse, we want to inverse the source term of the right-hand side term fxt. So given the solution of U, we want to, and so basically the U is given and the alpha t is given, we want to inverse the fxt. So the exact solution is U equal to t cubed times sine x, and the alpha is between 0 and 1. In this setting, we want to do the inverse problem. So we want to inverse the f. The f have an exact representation, so we want to matching with this exact f source term. So we're using similar number of training points, and the L2 arrow is equal to 0.0019. So the left is the ground truth, and the right is our approximation. So that you can see this is basically the f. So this is the x and the t, and the y z coordinate is the f. And this is the left. On the right is our predicted solution of the source term. So they give you very close representation. So we can achieve about like 10 to minus 3 accuracy in the L2 relative arrow. So the following, we're gonna look into basically we're trying to inverse. You can say we inverse the alpha. So we want to inverse for the PDE. We want to, instead of we inverse f, in this case we want to inverse the alpha t. So basically, given the f, given the observation of the u, and we want to inverse of the alpha. So I think this is a small challenge, right? Because we want to get the alpha t. So here is basically we want to build the loss function, right? So we want to train and also be able to infer where the alpha t is. So in this setting, so the exact solution, the alpha t equal to the half sine square t, and we're using 10,000 training points, and the L2 arrow is about 8.8 times 10 to minus 6, and then the x basically the number of epochs, and the y is the loss function. So you can see the convergence, right? There's a little oscillation, right, around the initialization. Then we be able to converge quickly. And on the right-hand side, we basically compare the ground truth alpha compared with our predicted alpha. So this, the matches pretty well. So this is the inverse problem. So next, we're gonna look into basically want to predict the solution uxt. So consider the alpha will be not just a function of t. The alpha will be a function of x and the t both. So that's more challenge because that basically represent the localization, right? So the first order will be a localized property. So it's a function of both x and t. So in this problem, we want to predict a forward problem given the fractional order, right, which is a sine x times t square, and the right-hand side fxt, and we want to predict what the solution u is. So that is, basically the fractional order is spatial temporal random field, spatial temporal field here.
Guang, can I ask you a question? Is this a well-posed problem because at t equals 0, alpha is 0, therefore you don't have derivative. So
it's a steady state, right? At that point, right?
yes. So
for that setting,
so you're not. How do you if that at t equals 0, there's no time derivative? How do you impose initial condition?
that is the 0, right? So in that case, let me go next slide. Let me see. I think for this one, I think if the start from 0, right? Because if you saw the f, if x equal to 0, the sine x equal to 0, right? So basically f equal to 0 at when at the end point, right? So when t equal to 0, this f also 0, right? That means the solution will be 0, right? Then the Laplacian operate on that, so give you 0 solution at the when t equal to 0, right? If you start from 0 initial condition.
But so I don't see initial condition here, so you don't need the initial condition.
I mean, the initial condition here, right? I think this is the
Oh,
U.
sorry. Yeah, you have zero initial condition. Yeah.
Yeah, so I think that way, I think it satisfies the initial condition because f is equal to 0, right? So basically 0, this is basically Laplacian equal to 0, that give you 0 everywhere, right, when you're starting, right? Then the time derivative when the alpha, right, kick in, then you can change back.
No, so you have an equation now. You have an equation which is 0, the Laplacian is 0. Because the left-hand side becomes a function at alpha equals 0. So it's basically ux comma 0 is equal to the Laplacian.
Yeah.
And then, so that's at t equals 0. So then basically you have, okay, yeah, that's a compatible solution, but yeah, that's a compatible solution.
Yeah.
So it is solvable. Yeah, it is solvable.
Yeah, it is solvable because yeah, we have an analytical solution for this case. So yeah, it's solvable. Yeah.
What do you do with the boundary condition, by the way, here? Periodic or
Yeah,
okay.
periodic. Yeah, because sign. Yeah.
Okay.
Yeah. So yeah, so we using also 10,000 point times 2 training points. And so here's the exact solution you can see because the exact solution is a sine x times t to the cube, right? T cube, right? So the sine x basically is the periodic boundary condition, you can see, right? So also when t equal to 0, the exact solution is 0. So that's how you say because yeah, so basically the solution is periodic, and also yeah, so that's the left is the exact solution. So in the middle is our DeepONet prediction. On the right is the arrow, absolute arrow. So you can see the L2 relative error is 5.5 times 10 to minus 5. So this is the try to inverse a fractional order, right? To predict the solution. This is forward problem. So the next we want to do is to try to do an inverse. We want to do an inverse for this fractional order, which is a spatial temporal. So we want to inverse this alpha, given the exact solution u equal to t cubed times sine x. So this is the fxt we assume, and we want to inverse the alpha. It's a much challenge because the alpha is a spatial of space and time. We want to do the inverse problem, and here is the solution. So you can see the left, the alpha t, the exact alpha t is 0.5 times sine x times t. And the middle is our approximate solution. On the right is the absolute error. So you can see this L2 relative error we can achieve around 3.16 times 10 to minus 5. And so that's what we get here. So let's see. So the following we're going to look into is to look into the fraction PD with fraction order alpha that, we want to predict the right-hand side f, which is a function of x and t. So the idea is we want to, given the u, right, and also the alpha, we want to predict the right-hand side is f. The f is will be a spatial temporal function. So that's what we want to do with 0 initial condition. And the boundary condition is periodic. So in that sense, we want to, so this is the exact solution for the f. So we want to inverse. So on the left is the basically represent the ground truth of the source f as a spatial temporal field, the xt and the source function. On the right is our approximation prediction. So the L2 error is around 0.016. So that's basically showing that our fractional DeepONet be able to inverse this source term accurately. So the following we're gonna look into is to predict the fractional order alpha and as a function of x and t and the noise scenarios. So we studied the basically want to inverse this alpha xt, but subject to 10% noise add to the right-hand side of the f. So we add to the f, then we try to study how this function responds to inverse this alpha. So here is basically showing you the ground truth is the 0.5 times sine x times t. In the middle is our approximation of the alpha as a function of xt. On the right is the basically the arrow, absolute arrow. So the L2 relative arrow is around 3 times 10 to minus 4. So this is the dealing with the noise situation. So the following slide we're going to show is to predict the fractional order PDE of U in the two-term fractional PDEs. So I think this is one of the quite challenging cases. So we have the first term, we have the alpha will be a spatial temporal alpha between 0 and 1. The second fractional derivative beta is also a spatial temporal field between 1 and 2. And if we are given of the F, and alpha and the beta, and we want to predict what the solution U is. So this is the setting. We want to, using fractional PINN-DeepONet, be able to predict the solution of the two-term fractional PDE. So the exact solution U is equal to the T cube sine X. And on the left is basically the exact solution. The middle is our approximation solution. And on the right is the absolute arrow. So you can see this L2 relative arrow is around 10 to minus 3 relative arrow. So this is the two-term for the forward problem, a predicted solution of the spatial temporal two-term fractional PDE. Then the next we're going to show you is the inverse problem. We want to inverse the alpha. So we'll consider the fractional, but there's a catch here. We want to study what happened, the fractional order is discontinuous. So we design a fractional order alpha, want to study what if our fractional order is not a smooth function, it's a discontinuous function, and how it can affect when we use it to do inverse problem. We want to, given the U and the F, right? Can you inverse not a discontinuous fractional order? So that's what we design. So the ground truth alpha will be equal to, if t between 0 and 0.5 is equal to t, if from 0.5 to 1 is 0.9, otherwise it's 0. So that's the way we bounded this alpha is between and 0 and 1. So our goal is try to be able to predict the discontinuous fractional order. So on the right, basically showing you how this alpha looks like. So the alpha will be, gradual linear grow, right, between 0 to 0.5. Then it gonna jump to, this is 0.9, 0.8, and 0.9, then suddenly become 0. Okay, so this is the discontinuities. So we have a discontinuity point around the 0.5. So this is our discontinuity function of the alpha. And so you can see, so the blue line is our approximation. The red is the ground truth, right? So you can say we can approximate even at the discontinuity point pretty well. Although we have like, 3 discontinuity. So on the left, at the 0, at 0.5, at 1, we have 3 discontinuity points here. And on the left, is showing you the loss convergence plot is a function of the number of epochs. And the L2 arrow around like a 10 to minus 3. So this is an inverse for the alpha. And we also did a study is consider the fraction order. We want to predict, inverse the discontinuity function of the alpha. So you can see this is this fractional order. So we changed the fraction order to be a more complex case, because before it's like just a linear or constant curve, right? So in this setting, we make the alpha is much more complex, become a sine function. So if the x, also we extended this, if the x is between 0 and 2, so it will be equal to half sine x times t squared. Otherwise equal to half, right? So we did design this much more complex, the alpha representation. I want to make sure our inverse solver be able to solve this discontinuity function of fractional order alpha. So in this study, we basically represent here is, the left is the ground truth, which is alpha equal to 0.5 sine x times t. And so you can see, so the matches, so the arrow, L2 arrow is around, a 4 times 10 to minus 3. So this is the inverse of the complex of the fractional order alpha. So the following I'm going to show you is a summary of this presented work. So in this work, I basically show fractional PINN-DeepONet can learn from both data and the fractional physical law to predict the accurate fractional PDE solution. And also, it can efficiently handle large-scale complex inverse fractional problems, and it can significantly reduce the computational cost associated with solving the fractional PDEs. And also, it can solve different type of fractional PDEs with various bounding conditions and initial conditions, and the different source term and the different alpha. And also, it can complement existing numerical method in solving fractional PDEs. And so I demonstrated I have solved a series of fractional PDE problems, and here's a paper. So if you're interested, you can access our preprint from this link. And finally, it's some future work. So we are working on trying to apply the fractional PINN-DeepONet to solve challenging real-world fractional applications. And also, we are currently developing a multi-fidelity fractional operator learning approach to tackle challenge with multi-fidelity data sets. Yeah, thanks for your attention. So any questions?
Thank you so much for your great talk. Now we open
Here's
the
some reference. Yeah.
questions. Do we have any questions for the speaker?
Guang,
Yeah.
at t equals 0, you keep getting that disagreement. Is it because at t equals 0, there's a singularity in the fractional derivative?
Yeah. I think so. Yeah. So here, for example, right? T equal to 0. Yes.
Yeah, in all the comparisons. Yeah.
Yeah. I think yeah, there's some singularity there. Yeah. Yeah, because there's discontinuity there. Yeah. Yeah.
So to capture that, you need to so you have a uniform grid in T, right?
Yeah. Right now we have uniform grid. Maybe some adaptive in time might help.
Yeah. So you can do adaptive in time for a little bit.
For a little bit. Yeah.
And
Then yeah. That needed some like a posterior, like some adaptive strategy there. Yeah.
But also Lingu, and also
Mm-hmm.
I had one student who we did the Monte Carlo.
Oh, okay.
So you estimate all these derivatives using Monte Carlo sampling.
Oh, I see. Okay, that will be perform very well for the high.
So you don't need the grid, yeah.
Yeah.
So this is actually goes back to 2 papers by Potlubny. In fact, if you look at MATLAB, those are implemented now. So you don't use the L1 formulas or the L2. You just use Monte Carlo sampling. So
Okay.
it's in the true spirit of pins, because you don't need to have grid at all, the auxiliary grid.
I see. So yeah. So basically, they can do they using auto differentiation or something to be able to do that?
No, because the
Oh,
derivative is an integral, right? So the integral is computed using Monte Carlo.
I see. Okay. Yeah.
And then you can sample, very heavily at that t equals 0.
Oh, I see. Okay. So that's a Linguist paper?
Yeah, Lingu wrote the first paper on that, but actually it's based on Podlubny. Podlubny is the guy who introduced the first book on numerical methods for fractional PDEs.
Okay. Yeah. I will look into it. Yeah, I think it will be useful. Yeah. Yeah.
So this avoids the use of grids, because that's what we tried to do in at that time when we did the paper with Goffey, we didn't know, that was not available actually. But
okay.
it turns out that yes, since these are integrals, can be computed with. Actually, we did it with quasi Monte Carlo, which is much better.
I see. Okay, so that basically become a match-free method, right?
Yes, exactly.
Yeah. So naturally integrated with the neural network, right?
Yeah, exactly. Yeah, that's the point. Yeah.
Yeah.
Ping and Nazanin did work on fractional for pharmacology, but she also used the grid spacing.
Yeah.
I see. Okay. Yeah, I will look into these papers. Yeah. Okay. Yeah, I think it's very interesting. Yeah.
Any other questions, comments? Okay, thank you so much for your
Yeah,
great.
thank you.
Yeah, it's
Okay.
time to close the session. Thank you everybody for joining us today. Have a great weekend ahead.
Yeah. Thank
Bye.
you, Guang.
Thank you. Thank you, George. Talk to you
Yeah.
later.
Bye-bye.
Bye.
Bye.
Bye.